Section 8.5, translation. Translation is the converting of the messenger RNA message that was made in the nucleus into an amino acid chain or a polypeptide at the ribosome in the cytoplasm. One or more polypeptides would make up a protein, and the four nucleotides, RNA nucleotides, adenine, guanine, cytosine, and uracil, are used to code for or create 20 different amino acids that will be used for protein synthesis or formation of a protein. DNA and RNA can be separated into 3-letter segments. These 3-letter segments would be used to create something called a codon. Okay, a codon is a sequence of 3 nucleotides that would code for a specific amino acid. An amino acid, remember there's only 20 amino acids. So amino acid can be coded for by more than one codon. There's 64 different codons. We'll get into those in a minute. But there's only 20 amino acids, so some of these would have more than one codon for a specific amino acid. Along with coding for the 20 different amino acids, one codon codes for something called a start codon. Okay, this codes for methionine, which is given by the codon AUG. So AUG on the messenger RNA molecule would bring in a start codon or a methionine. Translation always begins with methionine. Every protein synthesis starts with methionine. Most of the time it's removed when the protein gets it bent into its tertiary shape, but it's there to start. There are 3 different codes that would be stop codons, which stop codon would mean stop translating, stop building the protein, you're done. Okay, so there's one start codon, AUG, and 3 different stop codons. The genetic code matches each codon to its amino acid, one of the 20, or function. Function would be either start, one start, or 3 stops. Codons are always read without spaces as a series of 3 non-overlapping nucleotides. So here we got 3 nucleotides and 3 nucleotides and 3 nucleotides and 3 nucleotides. All of these would be located on messenger RNA. Okay, and this would code for 4 different amino acids: arginine, tyrosine, serine. Okay, if the reading chain shifted over 1, okay, these 3 bases would code for aspartame, threonine, and valine, different amino acids. But these 3 bases make up what's called the reading frame, the thing that's actually going to code for the amino acid. Any changes can result, or any changes can change the resulting protein. So, like I said, in reading frame 1, if this thing shifted over, these are the same bases all in order, other than it moved over 1. So we're getting a different series of amino acids in that protein. Regardless of the organism, codons code for the same amino acids. So this table right here is what's called the genetic code, or the universal genetic code for protein synthesis. This gives evidence that almost all organisms came from a common ancestor. Okay. The way you read this is these are our codons, these 3 base codons. This is methionine, or the start codon, right? So the first codon is all the way here on the left, reading in this column, A. And then we go to the second codon, U, that's in this column, U, and a third codon. So we go with this A, right? And this U, and then we look for G, which is in the bottom. So AUG codes for methionine. Okay, so first base, this column. Okay. Second base is right here, and third base is one of these guys, and that tells you what amino acid is coded for by that codon. Here is a problem for you. Suppose the messenger RNA molecule in the cytoplasm had 300 nucleotides. How many amino acids would be in the resulting protein? Okay, so the first 3, so if there's 300, okay, 300 nucleotides, that would be 100 codons. Why 100 codons? Because each codon is made up of 3 bases, and 300 divided by 3 is 100. Okay, so of this 100, the first one is a start codon. And the last one is a stop codon. So if we have 100 total, minus 1 for start and minus 1 for stop, how many amino acids be in the resulting protein? 98. So let's use this table on page 472 of your book, this universal genetic code right here. Okay, we're given a DNA sequence of TAC, GAA, ACA, CCG, ACT. Now we need to write what the messenger RNA sequence would be formed from that. So remember base pairing rules. When we're going from DNA to RNA, T would give us an A would give us a U, and DNA would give us a U on RNA. C is G, this would be C, U, U, this would be U, G, U, G, G, C, and U, G, A. So these are our messenger RNA codons. Now we're going to use these guys and this table to figure out where or what the amino acids would be from this sequence of codons. So our first one, AUG. First base is A, so we are in this row right here. Second one is U, so we're going to be in this row and in this column. So we're right in here. And our last one is G, so we're going to be here, and our first codon would be methionine, which is the start codon, which makes sense because all amino acids start with start. Okay, so second one, we're going to go to CUU. So C, we are in this row. U puts us in this column. And U gives us this one, which is the amino acid leucine. Okay, so that would be this guy. Start is this guy. UGU, again, we'd be in this row. U, G is all the way over here, so we're in this column. UGU is here, and that codes for cysteine. Next one, GGC. So G is this. C is here. Sorry. GG, so G is here. My apologies. GGC would be this, GGC, so it would be glycine. And last would be UGA. U is in this row. G is in this column. And A is here, which says stop, which makes sense because at the end of each protein would be a stop codon. Stop codon. So we start with methionine. There's our first one. Leucine, cysteine, glycine, stop. Done. There's our protein. So the site of protein synthesis is the ribosome. Now ribosomes can either be free-floating in the cytoplasm or embedded into the rough endoplasmic reticulum. Okay, ribosomes are the site of protein synthesis, and this is where amino acids are bonded together, okay, to form this amino acid chain, which will eventually become our protein. So ribosomes consist of 2 subunits, right? The larger subunit, this top part right here, has 3 binding sites for tRNA. So this would be the part of the ribosome made up of ribosomal RNA. Okay, this is the ribosomal RNA part. The small subunit binds to the messenger RNA. So this is what messenger RNA is going going to be attached to, and then its codons would match up with these anticodons on tRNA and hold it in place. Okay, so ribosome, site of protein synthesis, that's where amino acids are bonded together to make proteins. They have two subunits. The upper one has ribosomal RNA in it, upper larger. The smaller one, subunit, binds to messenger RNA. The transfer RNA, or tRNA, acts as an adapter between the messenger RNA, which would be getting read at the ribosome, and amino acids, which would be attached to the opposite end of the transfer RNA. So on the bottom of the tRNA is this thing called an anticodon. Okay, and that's a series of 3 bases, which would be the RNA complement to the codon on messenger RNA. At the other end is an amino acid, and this would be an amino acid that would be coded for by that specific codon. Okay, an anticodon is a set of 3 nucleotides that is complementary to a messenger RNA codon. It's a part of transfer RNA. Messenger RNA sequence of GGG, CAU, UUA, CCG would give us a tRNA sequence of what? Remember, this would be RNA complement. So that would be C, C, G, U, A, U, and G, C. These guys would be the RNA complement to the messenger RNA. Okay, these would be codons. These would be anticodons. Codons are on messenger RNA. Anticodons are on transfer RNA. Step 1 of translation. The ribosome would bind to a messenger RNA. So here's the ribosome. Messenger RNA is going to get threaded through it. It's going to bind to it. Remember, messenger RNA was made in the nucleus and leaves the nucleus to go to the cytoplasm. Okay, the tRNA, the anticodon on tRNA binds to the start codon on messenger RNA. Okay, so here it is. This would be our first DNA bonding to the start codon on this messenger RNA. Okay, step 1. Step 2. The ribosome is going to pull the messenger RNA strand the length of 1 codon. So it's going to bind with it, and it's going to start pulling it through until it reaches a start codon. 3 bases at a time till we get a start codon. The transfer RNA anticodon is going to bind with the messenger RNA's start codon and bring in this amino acid, methionine, which is always the first one in a polypeptide chain. Once that's attached, it'll pull it through 3 more bases, and we'll get to the next codon, which would be this, right, whatever it is. In this case, it's coding for leucine. So this will get held in place. These two are held together. These things are in close proximity, where this bond will happen from leucine to methionine, and we have 2 amino acids in our chain. This will continue and continue and continue and continue all the way through until it reaches the end, or the stop codon. We keep adding amino acids to the chain until it is complete. Step 3. As the bonds between the amino acids form, okay, the tRNA is pulled off, right? So, and it just leaves, it's pulled off the codon, and it just goes out to the cytoplasm to find another amino acid that would match up with its anticodon. Okay, a complementary TNR molecule binds to the next exposed codon, so this would be the next anticodon. It's going to bond with this codon. This guy's going to fit right in here, and it's going to bring in this amino acid to add onto our chain. So we have this thing continuing to go, methionine, leucine, and then cysteine, and so on, right? So this guy's going to come in here, okay? Once it's in there, this will bond to the growing chain. This tRNA would leave. right? The next one will come in, and so on and so forth until we hit a stop codon. Once the stop codon is reached, there's no amino acid there, and so the ribosome releases the protein. Okay, now most proteins undergo some type of modification in terms of folding into their final shape. So the protein will have to get processed a little bit, but as far as the actual amino acid chain, once it hits a stop codon, it's done, it's all there, and our protein is finished.